In this figure, a file system containing a shared file is shown. We have users A, B, and C. These are the user directories under the root directory. And under each user directory, we have several files and directories. And here notice that there is a file which is under a subdirectory of the user C, and it is shared by the user B. If the files are shared, the file system itself is now a directed acyclic graph, or DAG in short, rather than a tree. Having the file system be a directed acyclic graph complicates maintenance. If B or C adds new blocks, how does other owner find out? The solution is to use special inode for shared files, which indicates that file is shared. Or use a symbolic link, which is a special file. It is put in B's directory. If C is the owner, it contains the path name of the file to which it is linked. If C removes file, B's directory still points to inode for shared file. If inode is reused for another file, B's entry point to wrong inode. Solution is to leave inode and reduce number of owners. Here there is an example. Part A shows situation prior to linking. Here in user C's directory, we have a file for which owner is C and count is 1. This is the file. After link is created by B, in B's directory, we have a link to the file. Here it is saying owner is still C, but the count is now 2. It is incremented by 1. And after the original owner removes the file, it is shown here. In B's directory, there is a link to the file saying owner is C, but now count is 1. Symbolic link solves problem. When the owner removes the file, it is destroyed. Subsequent attempts to use the file via a symbolic link will fail when the system is unable to locate the file. Can have too many symbolic links and they take time to follow. The big advantage is that it can point to files on other machines. Log structured file system, shortly LSF. CPUs are faster, however, disks and memories are bigger. They are much bigger, but disk seek time has not decreased. The bigger one is cached for the smaller and faster one. And after that, the system can do reads from cache instead of the slower device. We want also to optimize writes because disk needs to be updated. In most file systems, writes are done in a very small chunks. Small writes are highly inefficient since a 50 microsecond disk write is often preceded by a 10 millisecond seek and a 4 millisecond rotational delay. With these parameters, disk efficiency drops to a fraction of 1%. To make the operation faster, structure entire disk as a big log, collect writes in a memory buffer, and periodically send them to a segment in the disk. Writes tend to be very small. Segment has summary of contents, inodes, directories, blocks, etc. Inodes are now scattered all around the disk, needs to be located. Keep inode map on disk and cache it in memory to locate inodes. Logged file system has a cleaner thread that spends its time scanning the log circularly to compact it. The cleaner moves along the log, removing all segments from the back and putting any live data into memory for rewriting in the next segment. Writer thread writes current ones out into new segment. Consequently, the disk is a big circular buffer with the writer thread adding new segments to the front and the cleaner thread removing old ones from the back. LSF, log structured file system, works well in Unix. It is not compatible with most file systems. It is not a heavily used approach. In the Journal of File Systems, aim is to guard against lost files when there are crashes. Consider what happens when a file has to be removed in Unix. Remove the file from its directory. Release the inode to the pool of free inodes. Return all the disk blocks to the pool of free disk blocks. If there is a crash somewhere in the process, you have a mess. Keep a journal, that is, list of actions. Before you take them, write the journal to disk, then perform actions. It can recover from a crash. Need to make operations idempotent, which means they can be repeated as often as necessary without harm. Must arrange data structures to do so. For example, to mark block N as free is an idempotent operation, while adding freed blocks to the end of a list is not idempotent. This can be repeated several times, having the same result. However, if this is repeated, the result is different. NTFS in Windows and Linux use journaling. Virtual file systems. In virtual file systems, we have multiple file systems on the same machine. Windows specifies file system drives. Unix integrates into virtual file systems. Virtual file system calls comes from users, then lower level calls are sent to actual file system. It supports network file system so that file can be on a remote machine. In virtual file system, a user process calls virtual file system through the virtual file system interface. The file system is called and then the files are accessed. Here it is explained how the virtual file system works. File system registers with virtual file systems, for example at boot time. At registration time, file system provides list of addresses of function calls the virtual file system wants. Virtual file system gets information from the new file system inode and puts it in a virtual node, makes entry in file descriptor table for processes. When process issues a call, for example a read, function pointers point to concrete function calls. In the virtual file system, suppose that there is a read operation on a file. From the file descriptor FD table, the virtual node is found, and then from the virtual nodes, we have a pointer to function pointers from which the pointer for the read operation is found. And then we have a call from the virtual file system into file system 1. And in file system 1, the read function is executed. For the file system management and optimization, in the disk space management, the block sizes are optimized. It is handled keeping track of free blocks and disk quotas, and also provided the file system backups and file system consistency. Furthermore, file system performance is optimized by using caching, block read ahead, and reducing disk arm motion, and also defragmentation of disks are handled. For disk space management, we use fixed size blocks which don't have to be adjacent. If stored as consecutive bytes, and file grows, it will have to be moved. So what is optimum, that is good block size? We need information on file size distribution. We don't have it when building file system. Tannenbaum et al., his group, in 2006 studied the file size distribution in the computer science department of a large research university, the VU, in 1984 and then again in 2005, as well as on commercial web server hosting a political website. Here, percentage of files smaller than a given size in bytes are given. In the first column, length of the files are given. This is the percentage of the files smaller than this size by the year 1984. And here is the percentage for 2005 and also for web. Notice that while it was 1.79% in 1984, it became 1.38 for 2005, and in web the size of the files are smaller, so the percentage is larger. For length 2, it becomes 1.88% for 1984, and it is 1.53 in year 2005, and it is 7.68 for web. And for example here, it is the percentage of the files less than 1 kilobyte, and it is 48% for 1984, 30.9% for 2005, and 48% for web. And it is 75% for 1984, 59% for 2005, and 70% for web. And if we look for about 90% of the files, consider this line, for example, it is about 32 kilobyte. 97% of the files in 1984 is smaller than 32 kilobyte, and it is 75% for 2005, and it is 91% for web. For example, in 2005, it is observed that 59% of all files at the VU were 4 kilobyte or smaller, and 90% of all files were 64 kilobyte or smaller. The median file size was 2,475 bytes. Some conclusions from this data are: with a block size of 1 kilobyte, only about 30 to 50% of all files fit in a single block. Whereas with a 4 kilobyte block, the percentage of files that fit in one block goes up to 60 to 70% range. With a 4 kilobyte block, 93% of the disk blocks are used by the 10% of the largest files. This means that wasting some space at the end of each small file hardly matters, because the disk is filled up by a small number of large files, videos, and the total amount of space taken up by the small files hardly matters at all. Even doubling the space, the smallest 90% of the files take up would be barely noticeable. On the other hand, using a small block means that each file will consist of many blocks. Reading each block normally requires a seek and a rotational delay, except on a solid-state disk. So, reading a file consisting of many small blocks will be slow. Consider a disk with 1 megabyte per track, a rotation time of 8.63 milliseconds, and an average seek time of 5 milliseconds. The time in milliseconds to read a block of k bytes is then the sum of the seek, rotational delay, and transfer times. Notice that controller overhead is ignored. The time required is 5, which is the average seek time, plus 4.17. This is the average rotational delay, plus to read block of k bytes divided by 2 to the 20, because we have 1 megabyte per track, and it is multiplied by 8.33, which is the rotation time. The dashed curve with the left-hand scale, which is data rate, megabyte per second, gives the data rate of a disk. The solid curve, this one, with the right-hand scale showing disk space utilization in percent, gives the disk space efficiency. All files are 4 kilobyte. Notice that as the block size increases, the data rate also increases, and the disk space utilization decreases as the block size increases. So, bigger block size results in better transfer utilization but worse space utilization. Trade-off is space versus data rate. There is no good answer. Disk space is hardly in short supply anymore. There is no good answer to choose which size. Disk space is hardly in short supply anymore. Historically, file systems have chosen sizes in the 1 kilobyte to 4 kilobyte range, but with disks now exceeding 1 terabyte, we might as well use large, for example, 64 kilobyte block size, as disks are getting much bigger. Hence, wasting disk space is generally more accepted. Keeping track of free blocks. The possibilities are storing the free list on a linked list as shown here in part A, or as a bitmap. The numbers given here are showing the blocks which are free. So 42, 163 are free, etc. At the end, in the disk block, we have a link to the next block showing the other free disk blocks. As we have more free blocks, we have more blocks to contain the free block numbers. For example, here, the free disk blocks are stored in blocks 16, 17, and 18. An alternative is to use a bitmap. Here we have a bit for each block, and the value 1 is showing that it's a free block. For example, block 0 is free, block 1 and 2 are not free, 3 and 4 are free, 5 is not free, etc. With a 1 kilobyte block and a 32-bit disk block number, each block on the free list holds the number of 255 free blocks. Notice that this is one less than what is available on the block, since what slot is required for the pointer to the next block. Consider 1 terabyte disk, which has about 1 billion disk blocks. To store all these addresses at 255 per block requires about 4 million of 1K blocks. If bitmap approach is used, a disk with n blocks requires a bitmap with n bits. Free blocks are represented by ones in the map, allocated blocks by zeros, or vice versa. For our example, 1 terabyte disk, we need 1 billion bits for the map. which requires about 130K of 1 kilobyte blocks to store. It is not surprising that the bitmap requires less space, since it uses 1 bit per block versus 32 bits in the linked list model. Only if the disk is nearly full, that is, has few free blocks, the linked list scheme will require fewer blocks than the bitmap. When the disk quotas for the users are considered, system administrator assign each user a maximum allocation of files and blocks, and operating system makes sure that the users do not exceed their quotas. Here in this figure, it is shown quotas are kept track of on a per user basis in a quota table. In the open file table for the user, for example user 8, we have here attributes disk addresses and user is 8, and the quota pointer points to quota table showing soft block limit, hard block limit, current number of blocks, number of block warnings left, soft file limit, hard file limit, current number of files, number of file warnings left. This is the quota record for user 8. Quota table is an abstract from a quota file on disk for the users whose files are currently open. When all the files are closed, the record is written back to the quota file. Warnings and errors can be generated when soft and hard limits are exceeded.